right, so we've talked about ions and how different ions are formed and how they're named based on their location on the periodic table. So now we're going to talk about something called polyatomic ions. So all the ions we've talked about so far are what are called monoatomic, meaning that they are a single element that gains or loses electrons to form a charge. But there are these ions called polyatomic ions. So poly meaning many, and what happens is these are covalently bonded together, and we haven't talked about covalent bonds yet, but think of them this way, think of them as counting as a group. So they're a group of elements with an overall charge, and you count them as a single unit, even though they're made of multiple elements. So naming those, they actually come from a table. There's a whole list of them, and there's some that, and we talked about this in the notes, so I'm not going to go over this in the PowerPoint, but there's some that you're going to be required to memorize, like sulfate, sulfite, phosphate, phosphite, nitrate, nitrite, carbonate, hydrogen carbonate, etc. You'll notice that a lot of them, particularly the ones that you're memorizing, a lot of them end in ate or ite. If it contains oxygen, it typically ends in either ate or ite. And kind of a helpful hint when you're trying to memorize them, the ite will have one less oxygen in it than the ate. So for example, sulfate is SO4, has a -2 charge. Sulfite is SO3. So notice how it has one less oxygen than sulfate. And you'll see the same thing with nitrate. Nitrate, NO3, negative. This is nitrate. Nitrite is NO2, negative. Same charge. And again, the whole thing, these count as a unit, so the charge is on the overall entire thing. There's one set that you're supposed to memorize that actually goes even further than just the ate and the ite. So chlorate is perchlorate is ClO4, negative. Think of like being hyperactive. So this is perchlorate. Then there's just chlorate, one less than the perchlorate. Then there's chlorite, and then there's hypochlorite. All of these have the same charge. So chlorate, perchlorate, chlorate, chlorite, and then hypochlorite. Now there are a couple of exceptions where they don't end in ate or ite. Typically that's because they don't have oxygen in them. One is hydroxide. It does have oxygen, but it is named with an ide. The other one is cyanide. It doesn't have oxygen, so it makes sense. There are others, I should say, but these are two kind of common ones. There's also one polyatomic cation, positive charge, that you're supposed to know, and that is going to be ammonium. There's another cation, but we're not going to use it. So ammonium is the only cation that you're going to be required to memorize, and then most of the other ones all end in ate and ite. So you'll reference those from the table. We talked about it in class, but I just wanted to explain what a polyatomic ion was. All right. So let's talk about when these actually get together. So we've talked about forming ions, but something can't just form an ion by giving an electron away to the air. It has to give the electron to something else. So typically when we get ionic compounds, what we have is a metal and a nonmetal. That's because the metals all want to give away electrons, and the nonmetals usually want electrons. And it also has a lot to do with electronegativity, if you remember that from the periodic table. The higher electronegativity means it really, really wants electrons, and low electronegativity really doesn't care anything about electrons. It's totally fine giving them away. And it turns out metals tend to have very low electronegativities, and nonmetals have very high electronegativities. And so when these get together, that forms the ionic compound. One of them will have a strong enough electronegativity to kind of steal the electrons from the other. Now in covalent bonds, in our next chapter, these are going to usually be things that have similar electronegativities. In fact, it's usually two nonmetals, and their electronegativities are very similar. Neither one really wants electrons to take electrons from the other in a strong enough way, and so they end up sharing instead. All ionic compounds are neutral. They are, in other words, the overall ionic compound doesn't have a charge. Even though it's made of ions, the charges on the ions have to cancel out. The bonds holding them together are called ionic bonds. They're very, very strong attractions. Also, we don't use the word molecule. Because of the fact that all ionic compounds are solid crystals at room temperature, they don't actually form individual molecules. Instead, we just use the lowest whole number ratio. If you see something that's a gas, carbon dioxide, can't be an ionic compound because it's a gas at room temperature. Water can't be an ionic compound because it's a liquid at room temperature. All ionic compounds are crystalline solids at room temperature. Now, it's not true the other way around. Not every solid is ionic, but every liquid and gas is definitely not ionic. We call the smallest ratio a formula unit. It's the smallest whole number ratio for an ionic compound. Covalent compounds, the smallest unit is a molecule. So when you think of water, for example, water is an individual molecule. It can be solid, it can be frozen as ice, it can become liquid. At room temperature, it's a liquid. But there's also water vapor, and it's a gas. And individual water molecules float around, in that gas form, and they float. That's not the truth about ionic compounds. Ionic compounds are all solids at room temperature. So NaCl is an ionic compound. But you're not going to find a single NaCl molecule, sodium chloride. What you're going to find is a block of sodium chloride molecules, like you see here for the sodium chloride. And so the smallest ratio, if we were to say, hey, what's the ratio of sodiums to chlorides in this molecule? It's 1 to 1. 1 sodium, 1 chloride. All right, so properties. Number 1, they have really high melting points. Because their bonds are so strong, their melting points are very high. Second, I mentioned this already, they're all brittle crystals at room temperature. They have very stable three-dimensional patterns. And they're really good conductors of electricity. I showed you a demonstration of this. If they're melted or dissolved in water. So a solid block of salt won't conduct electricity. But if I was to get molten salt, which would be over 1,000 degrees, by the way, or I dissolve some salt in water, then it will conduct electricity. I showed you a little light bulb up in class. In water, when we dissolve them, they are called aqueous solutions, which is going to come up a lot more in some future chapters. Right now, not super important. All right, so how do we figure out the formula? So remember, they have to be neutral, right? That means that the ratio of cations and anions have to cancel each other out. So, for example, let's look at this. So aluminum, if we go to the periodic table, which we've been practicing with this, and we figure out the charge on aluminum, it forms an ion with a +3, a cation. And chlorine forms chloride, -1. Right? So my overall charge here is +3. In order to cancel that, I need a -3. So what ratio of aluminums to chlorides would cancel the charge? Well, you would need 3 chlorides, right? 3 chlorides would give us a -3 charge. So our formula for aluminum chloride would be AlCl3. 3 chlorides for each aluminum ion. Now this is kind of confusing to do that way, the long way. So there is a shortcut called the crisscross method. You have to be careful here because remember, the formula is going to be the lowest whole number ratio. So you might have to reduce, just like you could reduce a fraction. For example, if you got a fraction of 2/4, you know, hopefully, from math, you can reduce that to 1/2. That would be the lowest ratio. So here's how we're going to do this. We're going to write the cation on the left, the anion on the right. The charges are always going to be a superscript, meaning they're up, up at the top. And then if we crisscross the charges, we can get the ratio. Now this is just a shortcut. And then our last step is we're going to reduce this if we can. So take a look. So here's our first example, calcium chloride. So calcium forms the Ca2+, chloride is Cl-. So here's how this would work. Calcium +2, bring your 2 down here, Chloride is a -1. Drop your 1 down here. And now our ratio is CaCl2. Notice we don't put negative charges here. It's not like this charge becomes a -1. We're just doing a shortcut to figure out. You could do this the long way. Calcium is 2 plus. Cl is minus. We have a +2 here, but we only have a -1 here. We need -2. So we would need 2 of these to get a -2. So it would be CaCl2. All right, let's look at our second one. Aluminum oxide. First thing, we look up aluminum. It forms a +3. Then we look up oxygen, find it on the periodic table. It forms oxide, -2. We crisscross our charges. So +3 becomes a 3 down here. -2, we need 2 of these to cancel 3 of these. And here's our formula, Al2O3. All right, one more. Lead 4 oxide. Okay, so lead 4 is going to be Pb +4. And oxide is -2. Again, you get that one from the periodic table. If we crisscross, you're not going to get the lowest ratio. Look what happens. Pb4 plus O2 minus. If I crisscross the charges, I get Pb2O4. Well, that's not the lowest ratio, right? 2 to 4 can be reduced to 1 to 2. So it would be PbO2 as our final formula. So here's what this would look like. All right, so I wanted you to try these 3 on your own. So you could pause it here if you want to do that. But I'm going to go ahead and work these out now for you. So sodium, we look it up on the periodic table. It forms a +1. Sulfide, that's going to be sulfur. On the periodic table, that forms a -2. Our shortcut, we're going to crisscross our charges. We're going to get Na2S. Notice we don't write the 1. I meant to say that earlier. So here is sodium sulfide. 10,4 chloride. So 10 has a +4 because of our Roman numeral. Chloride, negative. Crisscross our charges. We get SnCl4. And finally, calcium oxide. So calcium is a +2. Oxygen forms oxide, -2. Crisscross our charges. Now notice we get Ca2O2, but that is not the lowest ratio, right? That would be like having a fraction that's 2/2. So we're going to reduce that, and it's going to be CaO. Now this can also be done with the polyatomics in the same way. We keep them as a single unit, and we put parentheses around them. So calcium hydroxide, for example, is 1 calcium and 2 hydroxides. If you write this, CaOH2, this would be wrong, because this would be telling me there's 2 hydrogens, which is not the case. There's 2 hydroxides. Now, how do we get that formula? So calcium +2, hydroxide, you can put parentheses if that helps you, is a -1. Crisscross our charges the same way, we get CaOH2. All right, here's a polyatomic example. So aluminum sulfate. So aluminum is a +3, sulfate is a -2. We crisscross our charges. We got to put parentheses around the sulfate. When we crisscross here, it's a little confusing the way this one is done. We're going to get Al2SO43. All right, here's these. Iron 3 carbonate. So iron carbonate. Crisscross the charges. We're going to get iron here, and then carbonate, we need our parentheses, and it's going to be that. Calcium nitrate. Calcium nitrate is a -1. Crisscross, CaNO3, ammonium sulfate. Ammonium is a polyatomic. Sulfite is SO3 2 negative, you're going to get NH4, 2, SO4.